In this video, I'm going to talk about pie charts and scatterplots. Pie charts are pretty easy. All you do, and you probably wouldn't make one of these on your own. You would only use them on Google or make them on Google Classroom. But what you do is, let's say I recorded all of the type of animals you all had. So we have 25 people in here. So I recorded how many have cats, how many have dogs, how many have snakes, how many have, I don't know, chinchillas. And then the percentage of each would equal 100%. So if you have 100%, you're based on percentages. Pie chart is a very good way to go. And again, Google will do that for you once you learn how to use that. Where I'm going to spend most of my time talking is scatterplots. So a scatterplot is when you're learning to determine the relationship between two different things. So let's say, simple example, you record a person's shoe size and their age. So you have the shoe size of each person and the age of each person, and you will plot those. And you're going to look at the relationship between them. Is there a positive relationship between someone's age and shoe size? A positive relationship would mean that as one goes up, the other goes up. So as their age goes up, their shoe size goes up. Is there no relationship between them? So there's basically no relationship between shoe size and age. The other one is a negative relationship. A negative relationship would mean that as their shoe size went up, their age went down. They would go in an opposite direction. As one goes up, the other goes down. Shoe size and age, if you were doing kids from the time they were born until they're like 17, would probably be a positive relationship. As their age goes up, their shoe size goes up. Okay. What we call that when you're looking at the relationship is a correlation coefficient, which we use the letter R to represent. Now, to get an exact correlation between variables, you got to do math. We're not going to do a lot of math. We're going to do graphing, and then we're going to look at the graph we end up with, and we're going to guesstimate where that correlation would be. Would it be negative? Would it be positive? Would it be closer to zero? So if you ever take a statistics class, you'll learn how to do the math. Okay. But R can range from -1 to 1, including 0. A -1 would be a negative correlation, a strong negative correlation. As one variable goes up, the other one goes down. A positive correlation of +1 would be the strongest positive correlation. As one variable goes up, the other one goes up. As it goes down, the other one goes down. 0 would mean that there's no relationship between the two variables. Okay? There's no relationship between the two variables. Let's see what this looks like in a graph. And I'm going to skip to this page. Okay. Here you have a Pearson correlation of +1. +1, -1, and 0. True 0 probably in realistic terms don't exist in the real world. Okay. Here would be an example though. Let's say you graphed every person from the time they're born until they hit 18, let's say 20, just to make it easy, their shoe size and their age. So you graph shoe size, here's their age, here's shoe size. Doesn't matter what you put on each variable because you're just doing two variables. So there's 6 months, shoe size is here. 7 months here, all the way up to age 20. If it fell on a perfect line, as their age goes up, their shoe size goes up, and it fell in a perfect line, that would be a correlation of +1. To fall on an exact line like that is most likely not going to happen. A negative correlation, a perfect negative correlation, would be as one variable goes up, the other comes down. So let's say the number of police officers on duty in a city and the number of pickpockets. So if you look here, you have a lot of police officers and very few pickpockets. Where you have very little police officers, you have a lot of pickpockets, but it fell in a perfect line. Let's say we graphed 50 cities, and they fell on a perfect line like this, negative, as one goes up, the other goes down, that would be a perfect negative correlation. Again, in real life, that doesn't really exist. Okay. A correlation of 0, where there's no relationship. You look at this point, and you can't, there's no relationship between them. They're just I'll seem like random points all over the place. That would be a 0, correlation of 0. There's no relationship between the two. You can't predict. You can't determine one variable from looking at the other. Okay. Now, there are numbers in between these. Okay. So for example, 0.7. 0.7 is a positive correlation. So as one variable goes up, the other one goes up. It's a positive correlation. The line of best fit would fit through here. They're close to this perfect line, but not exact. So that's a strong positive correlation, but not a perfect correlation. That's more likely what shoe size and age would do. This is more realistic what it would look like. So it's positive 7. Okay. You can kind of see that as their age goes up, their shoe size goes up, but it doesn't fit on a perfect line. Okay. Same thing here. Okay. This is negative 0.5. As one goes up, there's a tendency towards a negative correlation. As one goes up, the other goes down. But it doesn't fit perfectly to the line, and the points are more spread out. So the more spread out they are from the line of best fit, the smaller the number. Okay. So here's 0.9, a negative correlation of 0.9. Not exactly on a perfect line, but a little more spread out. Okay. So here you see other examples. Here you have a correlation. It's slightly negative if one goes up, the other goes down, but it's pretty randomly spread out. Okay, it's pretty randomly spread out. So it kind of goes in a negative direction, but it's not a good predictor. Okay, there's not a strong relationship there. So what will happen when you go to Google Sheets is you will put in the numbers, the variables, so a person's shoe size and their age. We're going to do other ones, okay? Different variables. And then you will ask it to do a scatter plot, and then what will happen is you will see a relationship between the variables. And then you can put in what's called the line of best fit. Let me show you this. So what will happen is a line of best fit will kind of show you the tendency. So a strong positive correlation, here's your line of best fit between your variables. You'll see they're very close to that line. Okay, so that's going to be a strong positive correlation. This may be a positive 0.9. Okay. This one, the line of best fit is right here. The points are spread out a lot from that line. So this would be maybe a positive 0.3. Okay. Here you can't even put a line of best fit because there seems to be no relationship between the two variables. Okay. Here you put in a line, but the line of best fit is negative. So as one goes up, the other goes down. They're very close to the line, so this could be a negative 0.9. Okay. This one, again, it's a line of best fit that's negative, but the variables are very spread out, so it's going to be a weak negative correlation. Okay. Let me give you a practical application for this. So most of you in your PE classes at some point have either run a mile, let's say you've run a mile, and so you run a mile for time. Okay. Why are you doing that? Well, you're trying to predict, or your PE teacher is trying to give you information on your aerobic fitness, how well your body uses oxygen. Okay. To measure that directly, you have to put each person on a treadmill and you have to hook them up to a mouthpiece, and it takes about 15 to 20 minutes. And what you do is you make the treadmill go faster and faster. And as you can handle that, as it gets faster, your body consumes more oxygen. And you basically take the person up to the speed of the treadmill where they can't go anymore. And that would be like their maximal oxygen consumption before they pooped out. Okay. To do that for every person in a class of 30 people, first of all, it would be incredibly expensive. The equipment would cost tens of thousands of dollars. And it would take like the whole semester to test everybody. So what we do is someone did a study and they looked at the person's max VO2, which is the indicator of their aerobic fitness. They did that test on them, that expensive test, and then they had them run a mile. And what they found was they took their time to run a mile and their max VO2. And what they found was a correlation, let me go back to this, that probably looks something like this. That as your, well, actually it was a negative correlation. Let me do that. As your max VO2, okay, went up, as your max VO2 went up, your mile time was lower. Okay, your mile time was lower because the more fit you are, the faster you can do the mile. So what they found was probably a negative correlation, maybe something like this, a 0.9 between your mile run time and your max VO2. So what they can do is, based on your mile run time, they can predict what your max VO2 is, and they can give you an indication of how fit you are. So it allows us to test a bunch of people and quickly without spending a lot of money. So that's an example of how you can use correlations, okay, to look at the relationship between variables and how you can use it practically speaking. Okay. And you may have done another test. Actually, my master's thesis, my study was I looked at max VO2 and I looked at what's called a 20-meter shuttle test. How long you could keep up with the pace would determine your VO2 max. Okay. So that's how it can be used. So it's used a lot. But I will tell you this, and this is important. You can do something like this, but you cannot say that one causes the other. Okay. I cannot say that directly, if we did the study on like 100 cities and looked at number of police officers and number of pickpockets, I cannot say the number of police officers was the direct reason why there were less pickpockets. Okay. What correlations can do is they can show you the relationship between variables, and then you have to go beyond that. You have to do another study or several studies to show that one may be causing the other. Okay, so when answering scientific questions, it's step one of explaining natural phenomena, but it doesn't explain why. Okay, it doesn't explain why. So you'd have to take the study one step further. All right, so let me give you an example of how this. Let me give you an example of how this can be misrepresented. Okay, when looking at studies. So there's a strong positive correlation between the number of churches and the number of murders in a town. So if you took, let's say, 200 towns throughout the country and you plotted each town, you had a point for each town that had the number of churches and the number of murders, okay, you would probably end up with something that looked like this, okay, a positive 0.7. So as the number of churches went up, so did the number of murders. Okay, so how do you interpret that study? You can say there's a positive correlation between the number of churches in a town and the number of murders. But what you cannot say is that churches cause there to be more murders. So when people are going to churches, that's causing them to murder people. Okay, you cannot say that. Now, this is an obvious example. So why, in reality, is there a positive correlation between the number of churches and the number of murders? The reason why is because as a town gets bigger, you're going to have more churches and also more murders, but they don't cause each other. The churches does not cause the murders. Okay, so that's a real obvious example just to make it clear to you how you can use this and how you cannot. Okay, so we'll be doing some scatter plots. We're going to do them with your grip strength and flexibility just to kind of look at how this stuff can be used and how to interpret it.